In this video, we're going to look at binary numbers, and in particular at how you can go from binary to decimal and back again. So everything stored in the computer is essentially a binary number, which is just a sequence of individual bits where each bit is either a 0 or a 1. And this goes back to how things are stored in the computer. They're stored using hardware that is able to have one of two possible voltages across it. The low voltage is a 0, the high voltage is a 1. And so that gives us our binary representation. 1 byte is a collection of 8 bits, and then you can have collections of bytes, kilobytes, megabytes, etc. Now we've already seen that characters are represented using integers, so a given set of bits can have more than one meaning. It depends on the context. For example, this byte, this collection of 8 bits, if you think of it as an integer, it represents the number 97. But if you think of it as a character, it represents the character A. This sequence of 8 bits is either 70 as a decimal integer or uppercase F as a character. And they can have other meanings as well if you're dealing with other types of data. Usually when we're working with integers, we write them in base 10 or decimal. And in that representation, each column represents a power of 10. So for example, in the number 176, we have a 6 in the ones column, and it's the ones column because it's 10 to the 0 that is getting multiplied by 6, and 10 to the 0 is 1. The 7 is in the tens column, and it's the tens column because it's 10 to the first that's being multiplied by 7. And then the 1 is in the hundreds column. We're multiplying the 1 by 10 to the second. In binary, we're using base 2, so each column represents a power of 2 instead of a power of 10. We still have a ones column because 2 to the 0 is 1, and in this particular case we're multiplying that by 0 because there's a 0 in that column. We also have a 0 in the twos column, which is 2 to the first times 0. We also have a 0 in the fours column, and it's the fours column because it's 2 to the second. And we can keep doing this for increasing powers of 2. So 2 to the third is 8, 2 to the fourth is 16, and notice we have a 1 here, so it's 1 times 2 to the fourth. 2 to the fifth is 32, 2 to the sixth is 64, 2 to the seventh is 128. If you do the math here, you'll see that you get 176. So this is the binary representation of the number that we saw earlier in decimal. Now it turns out that the rightmost bit tells us whether the number is even or odd. If we have a 0 in the rightmost bit, it means the number is even. If we have a 1, it means the number is odd. To convert from binary to decimal, we can number the bits from right to left. The rightmost bit is bit 0, the bit next to it is bit 1, and we continue going from right to left. And then for any bit that is a 1, we're going to add 2 to the n, where n is the number of that bit. So in this case, we have a 1 in bit 6, so we're going to include 2 to the 6th. We have a 1 for bit 4, so we include 2 to the 4. We also have 2 to the third, 2 to the second, 2 to the 0. And when you add those powers of 2 up, you get 93, and so this binary number is equal to 93 in decimal. To go from decimal to binary, we have to figure out which powers of 2 need to be added together to produce the decimal number. And we're going to start with the largest power of 2 that is less than or equal to the number and work our way down from there. So for example, let's say we're converting 53. We want to know what is it in binary. Well, the largest power of 2 less than or equal to 53 is 32. And so we're going to start by saying we need that power of 2, and what's left over is 21. And then we're going to continue the process with whatever is left over. So in this case, we're going to break up the 21. The largest power of 2 less than or equal to 21 is 16, and we have 5 left over. We then want to break up the 5 into 4 plus 1. 4 is the largest power of 2 less than or equal to 5. And then finally, the 1 is itself a power of 2, so we're done. And so we end up needing 2 to the 5th plus 2 to the 4th plus 2 squared plus 2 to the 0. And so we're going to put a 1 for all of those bits. You can see we have a 1 for bit 0, for bit 2, for bit 4, and bit 5. And then we have to put zeros for bit 3 and bit 1 because their powers of 2 are not included. And so these 6 bits are the binary representation of the decimal integer 53.